Hey everyone, this is Eric Bricketto, teaching assistant for the Advanced LLM Application Building course available on Maven. And in this video, we are going to be walking through a Colab notebook that we recently demonstrated in class for how to take data and construct a knowledge graph from it, both in memory as well as in a graph database for persistence. And then how you take that generated knowledge graph and how you use it in both a traditional RAG and a graph RAG architecture within your overall LLM applications. You'll find that using graph RAG and an underlying knowledge graph can allow your LLM application to answer significantly more sophisticated questions through the power of multi-hop reasoning and the capacity to do logical operations on your data that you will not be able to get otherwise from a traditional vector database. So you can see in this particular Colab notebook, it's mostly basic stuff here, okay? So we are going to be taking care of our library installations and library dependency installations. Here we just need to be making sure that we are adding and specifying the environmental variable for OpenAI API key. Relatively common fare. This is nothing new. We're all used to this. We're going to be using the hotel reviews dataset from the Traversal AI Hackathon as the core of this particular notebook example. So we just make sure that we retrieve that particular dataset through the datasets library, load it into a pandas data frame, which you can see we have done here, and then let's take a look at the data that we have here to work with. You can see that we have columns for hotel names and descriptions, the names, specifically the titles of reviews, and any other text that corresponds to that review. The trip date for when the trip occurred, the URL of the individual hotel, the rating left in the review, the number of reviews for the hotel, the address of the hotel, the locality where the hotel is based, and the country where that locality is based, right? Now, let's talk about how you go about actually constructing this knowledge graph. So, if you recall when I was talking about knowledge graph construction in class, I mentioned the importance of organizing principles for identifying the data models that you need to be using for your specific business use case when you are constructing your knowledge graph before you've actually done the actual generation, right? Because especially in LLM-driven information extraction pipelines, not having an organizing principle may result in the extraction of who even knows how many entities and relationships, not half of which may not be entirely relevant to your particular business. Okay? We are applying that in this use case, in this example here as well. We start out by looking at our data, doing exploration of our data, and identifying the entities that we can extract from this. In this case, for the hotel reviews datasets, I have identified 4 obvious core entities, those being a hotel, a review left for a hotel, a locality, and a country, as well as another entity that can be derived from the existing features, which is specifically the trip period, right, when the trip actually happened for a particular hotel review. Once you have those entities identified, you need to do some basic text cleaning, text pre-processing, typical fare for any NLP processing pipeline and project, and doing some feature engineering in order to extract buckets for your trip period column. And once you have that, in this specific case, in order to keep the knowledge graph manageable, I have chosen to apply stratified sampling techniques from statistical analysis to the full dataset. What that does is it condenses down the datasets that we are working on for constructing this knowledge graph, while making sure that each of the categories, each of the strata of populations that are from our full dataset are maintained in equal proportion to what they were in the full data set when we are taking this sampling and into a sampled population of the full data set for our more manageable and more human legible purposes, okay? In this particular case, my default is to go with a sampling size of 7%, okay? Now, when we start out, we want to be doing some, like I said, basic feature engineering. We want to be doing some text pre-processing to remove special characters from the review text and title. We want to be taking the trip periods, which are in the original data set in the form of February 2020, June 2021, and so on, and we want to bucket those into seasons per year in order to keep the knowledge graph from exploding, right? Because you want to make sure that you are keeping your knowledge graph manageable, because it is easy for these graphs to explode in size as you add more data. And so in order to ensure that that is kept manageable, that is why I have chosen to do bucketing for the months and the trip periods into specific seasons per year, as I am doing here. Then we get into actually constructing the knowledge graph once we have completed our text pre-processing and feature engineering. You can see here I have chosen a sample size of 7%. I have specified colors and sizes of nodes for the individual node entities that will go into our knowledge graph for our own visualization purposes. Stratified it here, and then I am iterating through our stratified data frame and extracting the nodes and the relationships to add into the knowledge graph here. Specifically, we're doing it in memory for now using a NetworkX digraph data structure, okay? So we iterate through the sampled data frame, and then we start extracting and creating entity nodes for each of the entity pairs of columns and sets of columns from each row. Starting out here, we are creating a new node for the hotel using the hotel entity label. We are giving it the properties for the description, the hotel URL, an image and street address, its price range, as well as the name, and we are choosing to give it the locality as well as colors and sizes that we have already specified for hotels based on the dictionaries that we set up here. Moving on, we do the same thing for the locality, the city where the hotel is based. We add a new node for that into the graph. We do the same thing for the country entity. We add a new node for that into the graph with the country label. In the same way, we add a new node for the trip period. In each of these cases, making sure that what we are adding has not already been added, because we don't want to duplicate nodes. Again, making sure that each node exists once, uniquely, distinctly, and only once in the graph, and keeping the graph from exploding. So we are doing that here for the trip period. And then we add the relationships between the nodes that we have identified and added into the NetworkX digraph. Here we are adding relationships between the hotel and its locality for the located in relationship, and we are doing the same thing to add a relationship between the locality and its corresponding country, also giving it the located in relationship, okay? Then we finish it up by adding a node for the reviews itself, and adding relationships between hotels and reviews between reviews and trip periods for the has review and on date relationships, respectively. Once we have iterated through the data frame and we have added all of those nodes to the in-memory graph, then we visualize it. You can see that's what I'm doing here in this code block with the IPython and PyViz data libraries for visualization. We are creating an HTML that we can embed through an iframe to visualize this network using JavaScript. And so we end up getting a graph that looks something like this. So this is a pretty slick knowledge graph visualization that we have constructed here. Now, the next step in the process is to take this network that we have constructed and load it into a graph database for persistence so that we can do RAG on it. For this example notebook, we are doing that using Neo4j, which is the graph database that is one of the market-leading graph database providers and has probably the lowest barrier to entry in getting started. You can sign up on Neo4j's cloud platform to get a free AuraDB cloud instance of a graph database that can hold about 1 gigabyte to about 200,000 nodes in it for free. And we're going to be doing that for our purposes as well. So you will sign up here on neo4j.com to get started for free. If this is your first time signing up for and creating a database with Neo4j, you will see a screen that looks something like this. And if it is not, you will see a page listing your instances, something like this. So you will need to create a new instance here for yourself. Download the text file that holds your URI for the database instance as well as the username and password, and make sure that you are saving that text file somewhere safe, because we will be utilizing the credentials here very shortly. And then enter those credentials here in this cell. Here I have chosen to save the URI for the database instance into my Google Colab Notebook secrets, which you can see in here, where I have that saved here in this Neo4j URI environment variable secret. And then that gets pulled here to parameterize them. And then you paste in the password, although you could very easily do it by saving the Neo4j password here as well. Paste that in, and then you are connected. Next, we want to be making sure that we are adding the nodes and the edges from our network X in memory graph into Neo4j. That is what this code is doing here, to add the graph into Neo4j using a graph driver session. Okay, we have two operations that are happening here. First, we are merging in the nodes by their labels, and then we are merging in the relationships between the nodes that we have added in. These two are cipher statements designed to be able to take care of that for us, which is the database language of choice for graph databases, much as SQL is the language of choice for relational databases. So we run that. We make sure that it adds the entire graph into the Neo4j instance by passing in the G network X graph variable that we had constructed earlier. It'll take a few minutes for this code to finish uploading all of the entities and relationships into Neo4j, but once it has finished, then we can move on and create a vector index in Neo4j on the nodes that we've already added. Okay? Now recall when I was saying in class before that when we are trying to implement semantic similarity over a graph database and combine a knowledge graph with vector embeddings, the most common way that we do that is by taking the text properties from individual nodes, embedding them, and then adding those embeddings back onto the nodes as searchable properties for a semantic search. That's what we are doing here as well, and we are utilizing LangChain's support for Neo4j vector stores to be able to create that. We don't typically recommend being dependent on LangChain, but just to get people started with this for a quick and dirty prototyping, it is convenient to be able to use one of LangChain's interfaces and abstractions for this purpose. So we are utilizing the Neo4j vector class and generating a vector index from an existing graph where we pass in the credentials to the graph database instance. And we are choosing to create a vector index on the reviews, since those are the ones that have the most text in them that we want to be able to search on. We name that index with the reviews. We specify that it's supposed to be for the nodes with the review label specifically. We specify which properties on those nodes are the unstructured text nodes that you want to be creating embeddings for, and then we are giving it the name of the property that will hold those embeddings, much like I was talking about in class before. Okay, so we run this. Popping over into our console workspace for the Neo4j database instance that we had created before, and doing a basic query against the database to make sure that we actually have uploaded all of our data properly, we can see that indeed our knowledge graph has been sufficiently uploaded here. We have all of the hotels, the reviews, as well as the cities and the countries, so everything looks good there. And then we can do a basic sanity check to make sure that our vector index has been added properly. We can do that in here. Show vector indices. And yep, we do have a reviews vector index that has been added. Very good. And we can scroll down here and select any of these reviews, the review nodes that we had built that vector index on, and scroll down and we can see that there is indeed an added embedding property that holds the vector embeddings for the name and title text fields. So everything is looking good here so far. So now let's query the vector database and see whether we are able to get most semantically similar documents. And it looks like yes, we are able to get back semantically similar documents here. Moving on, we can spit this into a vector index RAG chain. Again, easy prototyping using LangChain. We're trying to teach you not to be dependent on LangChain, but just for the sake of demonstration purposes, we are using LangChain here. We are going to be spitting that vector index into a retrieval QA chain and running that, initializing that and running that here. So we run a query in some similarity search against the vector index. Here we are doing the Serdesi Mansion Hotel. This may or may not come back with matching reviews in your particular knowledge graph, only because of the stratified sampling that we did before. So we run that, we make sure that we are getting back proper semantically similar document snippets, then we are spitting that vector index into a LangChain retrieval QA chain. So we run that, ask the same thing, and we see that it is able to get back generated answers based on the semantically similar document snippets that were returned in the semantics into the similarity search. Moving on, let's now get into trying to do a graph rag and cipher retrieval. Okay, so we are going to be using LangChain again to connect to our Neo4j graph instance again. We are going to have LangChain refresh the schema so that the underlying model, the agent chain, knows the schema that is used in your graph database so that it can more accurately generate cipher queries to be able to navigate the subgraphs of facts in your Neo4j instance. We have initialized that into a graph cipher QA chain here, and then let's query it. So, as I mentioned in class before, GraphRag can be used to do a number of operations and more sophisticated reasoning that you can't easily get from a typical RAG setup in a vector database. First, you can run logical operators on the data. You can count how many reviews this particular hotel, the Romance Istanbul Hotel, has in the data set. This comes back with 3 from our stratified sample. You can likewise count the hotel that has the maximum number of reviews, and it will be able to do that proper counting and give you back the answer that the Astoria Estotel Hotel has the highest number of reviews in your knowledge graph. You can use GraphRag in this context to answer questions that require multi-hop reasoning, multiple steps in relationships, because you're dealing with networked data where those relationships and those multi-levels of relationships are the core of your data model. right? So you can ask a question, and I'm particularly happy about this sophisticated question, how well it does on this. You can ask, tell me what positive things were said in reviews that were left for hotels in San Francisco where the reviewer's trip date occurred in fall 2023. And you can see that the QA chain generated these cipher queries to be able to query that specific subgraph from the Neo4j database. It was able to get back the proper text, and then it was able to generate a good, solid answer from that navigation of the subgraph. And you can do this quite satisfactorily with other indirect relationship navigations and questions requiring that as well. For example, in this question, asking in general what reviews were left for hotels in the country of Turkey. And it will answer for you. Now let's show an example of how we can combine these two approaches together. Cipher-based graph RAG and regular vector database-based RAG. Okay? So again, using a LangChain strictly for prototyping purposes, we are going to create a new LangChain agent of the OpenAI functions type, and we are going to give it two tools that correspond to the separate chains that we created earlier. For the reviews tool, we are going to give it our vector QA chain and specify that this tool it will use when it needs to answer questions about hotel reviews. And then we will give it the graph tool, which will be built around the cipher QA chain. This tool, we will specify to the agent that it will use it when it needs to answer questions that require logical operations on hotels, locations, any sort of aggregation, anything like that. And then we spit those into a proper agent here. Then we can start asking it questions and test how well the agent does in distinguishing when it needs to query against its vector RAG tool and when it needs to query against its graph RAG tool. For this first question, we needed to search in the text descriptions of the individual hotels, since we did not specify in the properties of the hotel nodes the number of rooms that each hotel would have. So we ask it this question, it picks up correctly that it needs to use your graph cipher QA tool, it queries it, and tells you that it is indeed the Romance Istanbul Hotel. Similarly, we can give it a test question about reviews that should prompt it to use the review vector QA chain. And you can see here that it did indeed properly choose to use the reviews tool, and it came back with an answer pointing to two specific reviews that were negative about the Romance Istanbul Hotel. So at this point we're almost at the end. Now let's take what we have learned here and apply it to an information extraction pipeline for constructing a knowledge graph from unstructured text. As I mentioned in class before, there are two broad ways that you can approach the information extraction pipeline step. The first is using LLM-driven information extraction using GPT or Gemini or whatever. The Microsoft GraphRag library, as I mentioned before, utilizes that particular approach for constructing its knowledge graph. The other is to utilize more classical NLP techniques in order to do your knowledge graph construction. I have chosen to do the latter here, specifically by using the Diffbot service. Diffbot is a company that is focused on constructing the world's largest knowledge graph based on data from the open web. They have crawled effectively the entire internet, and I find their ontologies to be actually the most remarkable and impressive out of any knowledge graph solution that I have seen so far. They are particularly well suited for business use cases that deal with web data, such as doing web search when you need to construct a knowledge graph from a real-time web news article, or being able to mine opinions and entities from discussions in forums and discussion boards. as well as being able to construct graphs of entities and relationships in e-commerce platforms from product pages and product reviews. You will need to sign up for a free account on Diffbot in order to do this final part of the exercise. However, they offer a free tier that gives 10,000 credits of searching against their existing web knowledge graph, as well as their natural language API for extracting entities and facts from unstructured text, which we will be using here in a second. So in order to follow along, go ahead and sign up for a new account on Diffbot here. And then once you have done so and you have gotten to your dashboard for Diffbot, you'll want to copy your API token that is right up here on your dashboard, okay? Once you have done so, you can get back into the notebook and you can paste in your Diffbot API token there. And then this following code, these functions, are written to call and interact with the natural language API of Diffbot. And the natural language API takes in unstructured text and it will send you back lists of extracted entities as well as the extracted facts between the entities that were obtained from that text, the fact triplets that will go into your knowledge graph. We take each of the facts that we get back from the Diffbot natural language API and we upload them directly into our Neo4j graph database instance here using this set of APOC, essentially stored procedures, the equivalent of stored procedures in Neo4j using the APOC library to merge the nodes that we have obtained as well as the relationships between the nodes. In order to test this, we use a snippet from recent news about Anthropic and product releases that they have rolled out to the public, and the quotes from their leaders, their CEOs and founders about these new products, okay? We can see that we have specified that here. This is given as a news article type of document. We want to chunk it using LangChain recursive character text splitter, and then we just run our function, and it obtains the fact triples from the text using Diffbot's natural language API, and for each of those facts we upload it into our Neo4j database here. So, to summarize what we've done here, we've taken data, starting out with a tabular data set, and we have constructed a knowledge graph from it. We did that first in memory using the NetworkX library, and then we added that knowledge graph into a graph database such as Neo4j for persistence. Once we did that and added it into a DB for persistence, we built RAG as well as GraphRag query mechanisms on top of it, and we've shown that we can effectively utilize an LLM application on top of both regular RAG and GraphRag in order to answer questions about the underlying data that it would not have been able to do otherwise without the powers and the capabilities that knowledge graphs and GraphRag give us.